Bismillahirrahmanirrahim. Assalamu alaikum dear students. This is our next problem. Problem once again having been chosen from the book Modern Physics by Kenneth S. Crane. As usual, we first come to its statement. Okay, the statement is the equilibrium separation of hydrogen iodide. Okay, as we have dealt in previous problem, several elements having chemical name like chlorine, bromine, fluorine, etc. when make molecule with some other atom, their the nature of word chlorine takes the form as chloride, bromine takes the form bromide, iodine takes the form as iodide, and many other. So the equilibrium separation of hydrogen iodide is 0.160 nanometer. Nano standing for 10 to power minus 9. 0.160 nanometer, and its measured electric dipole moment is 1.47 into 10 to power minus 30 coulomb meter. Find the fractional ionic character of hydrogen iodide. This problem is quite similar to our previous problem. I think previous problem was regarding sodium fluoride. Okay, sodium fluoride, sodium and fluorine, and then sodium fluoride. This problem is about hydrogen iodide. Okay, remaining process is remaining method of solving problem is quite similar. Okay, as usual, we first come to its helping tools. Helping tool number one, the electric dipole moment. Dear students, we do not give a sufficient time to this tool because this tool has been discussed in our previous problem. Okay, so we skip this tool. Okay, we have discussed in detail in previous problem. Okay, tool number two is also a table of physical constants, and this tool has also been used several times in previous problems, so we also skip this this tool, helping tool. Okay, tool number three, there are two versions of this tool, and both versions have been included in previous problem, which was about sodium fluoride. Okay, so we skip these two versions of tool number three. Okay, now as usual, we first come to its solution, and this part of solution is also that part which was included in previous problem. Okay, we know that electric dipole moment of an ionic molecule is given as P equal to Q or EQ, where EQ stands for equilibrium and EQ is written as a subscript of capital R, where Q equal to E is equal to 1.602 into 10 to power minus 19 coulomb, and R equilibrium, EQ is written as a subscript of R, is the equilibrium separation of the ion using, dear students, Q equal to 1.602 into 10 to power minus 9 coulomb. This Q is the same as this value. Okay, and R eq is equal to 0.160 nanometer. This is given in the statement. Okay, we move for the time being to statement. 0.160 nanometer. Okay, the equilibrium separation of hydrogen iodide is 0.160 nanometer. Okay. This is using AQ is equal to this and R equal to 0.160 nanometer. Equation number 1 becomes, we have just put these two values in equation number 1, and equation number 1 takes the form as P equal to this into this. Okay, what we have done, we have just put these two values in this, and next there will be only simplification. Okay, how do we affect this simplification? Dear students, here in place of n we have replaced it with 10 to power minus 9. Okay, remaining no change in this step. Okay, this step is a continuation of this step. The only difference is that here in place of n we have used 10 raised to the power minus 9. Okay, and hence nanometer, from nanometer, nano has been eliminated and 10 to power minus 9 has taken the form. Okay, in the next step we have multiplied this value, that is 1.602 with 0.160, and this takes the form as 0.25632 into 10 to power minus 28 coulomb meter. Now we explain why this 10 to power minus 28. This is 10 to power minus 19, this is 10 to power minus 9. Okay, these two will contribute 10 raised to the power minus 28. Okay, 29, 19 plus 9 is equal to 28. Okay, this becomes equal to this into 10 to power minus 28 coulomb meter. Dear students, here to the extent of this result, our problem has been solved quite accurately. First part of this problem. Okay, but as in our previous problem, we had stated that in physics there are some trends, there are some fashions which we should obey, which we should follow, which we should adopt. Okay, otherwise this is not necessary. This value is quite correct, acceptable. Okay, the fashion or trend is that we express electric dipole moment in terms of 10 to power minus 30 coulomb meter. Okay, so for this purpose, when we will change 10 to power minus 28 into 10 to power minus 30, then this value, that is 0.25632, will take the form as 25.632. Okay, that is to say decimal has been shifted 2 stages ahead. Okay, instead of 0.25632 we have obtained the value 25.632. Okay, into 10 to power minus 30 coulomb meter. Okay, this part has been solved. Now we move to other part of this problem, in which a fractional ionic character is to be measured or calculated. Okay, as per tool, which tool had two versions. Okay, fractional ionic character equal to P equal to electric dipole moment measured electric dipole moment over Q capital R EQ. Here EQ is written as a subscript of capital R and EQ stands for equilibrium, and hence R stands for equilibrium separation. Okay, in the next step we have placed the value of measured electric dipole moment 1.47 into 10 to power minus 30 coulomb meter. This value has been given in the problem statement. Okay, we move back to show that this value has been given in the statement. Okay, 1.47 1.47 this. Okay, and its measured electric dipole moment is 1.17 into 10 to power minus 30 coulomb. Okay, so we have used this value here. Okay, okay, in the numerator there is only one term, and this term or this expression, this value has been taken from the statement. Moreover, in place of q r e q, we have taken this value. Okay, because according to question number 1, p is equal to q r ic. So this q r ic is equal to p, and we have found this value of p r q r equilibrium as this value. So here in the denominator we will use this value. Okay, so dear students, here 10 to power minus 30 will be cancelled with 10 to power minus 30. Moreover, coulomb meter will be cancelled with coulomb meter, and we will be left only with the number in the numerator and number in the denominator. And when we solve it using calculator, we get the result at 0.05735. Okay, dear students, we have found fractional ionic reactor as 0.05735. This implies that we will multiply it with 100, and that will be the percentage ionic. Okay, so when we multiply this factor with 100, then it will not remain 0.05735, rather it will become 5.735. Okay, 5.735% ionic. This implies that 5.735% ionic. Okay, this is sign of percent. So moreover, it is more appropriate to reduce it to 2 decimal places. Okay, however, it is quite acceptable, quite accurate. Okay, this is the end of our problem. Till next problem, Allah Hafiz.